All right, in this video, we're going to take a look at how to solve equilibrium problems when you might need a little bit more help with solving for x. And so in previous lessons or examples, we saw that it was pretty easy to solve for x. We could square root both sides, and it was a nice sort of linear equation to solve for. But sometimes we won't be able to do that, and we'll have to use other tools and techniques to solve for x when we can't factor, for example. So one great example of that, or one great tool that you can use when it's more difficult to factor and solve for x, is something you would have learned in earlier math courses, and that's the quadratic formula. If you don't remember the quadratic formula, you can watch a little video about it over here. But essentially, if you were to write out an equation in this form here, second degree form, ax squared plus bx plus c is equal to 0, and you want to find your x value, you can simply say that x is equal to minus b plus or minus square root of b squared minus 4ac over 2a, where the number in front of the x squared is the a, the number in front of the x is the b, including its sign, and the constant is the c, including the sign. And then generally, a would have a sign as well. If it was negative, it would be negative. If it's positive, it's positive. And so we can use this for solve for x in situations where it's more difficult to solve for x. We can't factor, for example. So every problem we're going to do here is very similar to what we've seen in previous problems. It's just that we'll have to solve for x using the quadratic formula. So if 0.5 moles of N2O4 is placed in a 1 liter closed container at 150 degrees Celsius, what will the concentrations of N2O4 and NO2 be at equilibrium? The equilibrium constant is K, 4.50. So let's do our setup first. That's our first step. We're setting everything up. We're making an ice table. I, C, E. Don't forget that this is going to be in molarity, moles per liter. And we don't have the molarity given to us right now for the N2O4. We have the number of moles, so we have to find the molarity with the moles in the volume. So remember that C is equal to N over V, which is going to be 0.50 moles over 1.0 liters, which is 0.50 moles per liter, or molar. So that means it's our initial concentration, 0.50. And we don't have NO2 right now because we didn't have any in the vessel. We just had the N2O4, the reactant. So at the onset, there's no NO2. So what is our change going to be? It's based on a molar coefficient, just as we saw normally. So we're going to use up some reactant, so that's minus x, and we're going to produce the product, so that's plus 2x. And so our equilibrium concentration for the reactant is going to be 0.50 minus x, and then for the product, it's going to be 2x. So now we need to, essentially the question is asking us to find what are these actual concentrations, not what is the expression with the x in it, but find the x and plug it in there to find the actual concentrations. So now we need to create a equilibrium expression. And remember, we have the K value given to us. K is equal to 4.50. So let's create a basic equilibrium expression first. So K is equal to the concentration of NO2 squared because of the 2 over the concentration of N2O4. No need to square it because there's just a coefficient of 1 there. And so that's our equilibrium expression. And so we can go ahead now and plug in the information that we have from the question into the equilibrium expression. So 4.50 is equal to 2x squared, because NO2 is 2x at equilibrium, over 0.50 minus x. Now, in previous questions, I could square root both sides to find my x pretty easily. But the problem here is that I can't square root both sides because this denominator is not squared. If I have squared and squared, everything is squared everywhere, then I could square root both sides, but in this case, I can't do that. So I'm going to have to essentially send everything over, expand, distribute, expand, and create a second degree equation, and then try to solve that. And you maybe want to try to factor it, but it might be difficult to factor just in your head. So you might need to use the quadratic formula. But let's take a look at what that looks like just to see. So let's continue this process here. We'll do 4.50 times 0.5 minus x is equal to, so 2x squared is 4x squared. And now we'll distribute everything and then send everything to one side. So 4.5 times 0.5 gives us 2.25 minus 4.50x is equal to 4x squared. And then we'll send everything over to the other side. So we'll get 0 is equal to 4x squared plus 4.50x minus 2.25. And you can rewrite this as this. So 4x squared, you're just flipping the equation around. You don't have to rewrite this way, but I just do because it's easier for me to understand what's going on. But it's the same idea. So this is our A, this is our B, and this is our C. So you can try to factor this, but again, it will be very difficult to do. So in this case, to solve for x, we're going to use our quadratic formula. And once we have x, then everything else is the same after that. We just have to plug in our x values into the equilibrium concentration expressions we came up with, and then that is going to help us find our equilibrium concentrations. So let's go ahead and do that. So we know that x is equal to minus b plus or minus square root of b squared minus 4ac over 2a. And so when you do this, you're going to get essentially two x values. And here's why. So let's go ahead and carry this out. Essentially, you're doing one of them is going to be a plus and one's going to be a minus, right? You're doing minus b plus this or minus b minus that. So let's plug everything in. So we have minus b is minus 4.50 plus the square root. And actually, what I'm going to do is I'm going to erase this. I'm going to first plug in numbers and then do the split, just so I don't have to write that twice, just to be more efficient. So x is going to be equal to minus 4.50 plus or minus square root of b squared, so 4.5 squared, minus 4 times 4 times negative 2.25, because the c is negative, over 2 times 4. And so this will essentially lead me to two possible outcomes. I'm just going to simplify what's in the square root as well. So let's do the plus outcome and the negative outcome. So you'll get negative 4.50 plus, so let's see, 4.5 squared minus 4 times negative 2.25 times 4. So plus the square root of 56.25 over 2 times 4, which is 8. Whereas here it's going to be the same idea, but it's going to be negative 4.5 minus the square root of 56.25 over 8. And so that means here x is going to equal 2 and x will equal 2. So let's see, square root of 56.25 plus minus 4.5 divided by 8. I get 0.375 over here. And then for the other option, so square root of 56.25 times negative 1 plus negative 4.5 divided by 8, I get negative 1.5. So I need to choose the better option here. They can't be both x values. So in this case, it's pretty straightforward. You'll get an x value that's negative, and chances are you're not going to want to use a negative x value. And you can go and try to experiment this. You're not really going to have a negative concentration, right? But if I put negative 1.5 into the x here, I get negative 3 molar, which doesn't make sense. Here you get a positive concentration. You do 0.5 minus 1.5, which actually gives you 2 molar. So you're higher than you were before, which doesn't make sense because you're using up the reactant. So that doesn't make sense either. But the real giveaway is that essentially you're going to get a negative concentration, which we don't want. So this one here is not plausible. So we don't want this one. And this one here is plausible. So this is the x we're going with to find the concentrations at equilibrium. So that's our last step. So this was step 4. Step 5, the concentration of N2O4 at equilibrium was 0.50 minus x. Let me just double check that. That is true. And the concentration of NO2 at equilibrium is 2x. And so remember, x is 0.375, and we're plugging that into here and into there. And so we'll get 0.5 minus 0.375. We get 0.125 molar, or according to the number of sig figs, so we need 2 sig figs. We'll round to 2 sig figs here. Because you have a 5 and nothing else, remember we round to keep it even, so 0.12 molar. And then here it's 2 times the 0.375, and that will give us 0.75 molar. And so these are our equilibrium concentrations for this system. To check your work, if you want to check your work, you can plug in the numbers you got into the equilibrium expression that you came up with and see if you get the K value given in the question. So I use the unrounded values. So for NO2 it was 0.75 squared over the N2O4 0.125, and we get 0.75 squared divided by 0.125. Whoops. And I get 4.5, which is what was given in the question. So therefore, those equilibrium concentrations are correct. And so essentially, as you saw, it was the same process that we did for other questions. It's just that now to solve for x, we had to use the quadratic formula. So I'd like you to try example 2 on your own. There will be a video lesson made to walk you through it, but you can find the examples in the link provided here, or the answers in the link provided there, just see that you have the right numerical answers. If you struggle with example 2, I recommend you retry it over and over again, but use my video to assess yourself to make sure you did all the steps properly. Keep your work nice and organized. So number the steps if that helps. Make your ICE tables as step 1. Keep all your given information in one area so it's nice and easy to access once you're ready to solve the problem fully.